In this video, we are going to take a look at Unit 7, Lesson 2, which is Inscribed Angles. So we're going to be analyzing angles that are made from chords. So at the end of this lesson, you'll hopefully be able to learn what you use what you learn about inscribed and central angles to determine angle measures in this diagram. So page 151 is where we're going to start with a notice and wonder. So looking at this diagram, what are some things you notice and what are some things you wonder? Take a minute to write down a couple and then come back to the video. All right, so you can certainly come up with a variety of things that you noticed here. Here are a few things that you could have noticed. Maybe you noticed that there are two chords in this diagram that are forming an angle. So you see this chord here and you see this chord creating an angle. You see that the chords define an arc. So these chords end at C and B and there's an arc highlighted between them. Maybe you notice that this orange angle is not a central angle because its vertex is not on the center of the circle. But if you were to draw in two radii, you maybe noticed that you could draw in a central angle. So some things you might be wondering about: what would happen if we moved point D? So if we moved this point around the edge of the circle, would that change the angle measures in the diagram? So if we were to move this, which would then move these chords, would that change the angle measures in the diagram? Is there a name for this orange angle? Is there a relationship between the orange angle and the central angle? And is there a relationship between the highlighted arc and this angle? So those are some things you might have noticed and wondered about this diagram. So in fact, yes, there is a name for this angle. And this angle formed by two chords is called an inscribed angle. So when it's formed by two chords that share a common endpoint. So not if the chord, not if our chords were here and here, okay, those aren't touching each other. But if they share that common endpoint, then you get this inscribed angle. And you can highlight this on your lesson summary if you'd like to, or you can write it in wherever you feel like it in your book. All right, then on page 151, you'll see this diagram, and it gives you some instructions. The first one is to draw point B anywhere you want, okay, on the circle, just not on the highlighted arc, okay? So don't put it over here, but anywhere along this part of the circle. So just go ahead, pick a spot for B wherever you want. And you need to measure this angle. So go ahead and take a protractor, measure your angle. Should be the same as mine. So seeing that it is 80 degrees. Whoops. And then go ahead and connect chords to angle to point B, okay, from the end of this arc. So go ahead and connect C to B and Q to B, and then measure that angle. So again, wherever yours ended up, and then measure the angle. So mine was 40 degrees. Okay. And maybe yours was 40 degrees also. So depending on where you drew your angle. So here's some different things. If you're doing this at home, you obviously don't have a group that you're doing it with. But here are some different possibilities that could have happened. So we had an 80-degree central angle, which meant that this arc was also 80 degrees. When B was drawn here, we get 40 degrees for this angle. when B was drawn here, we're getting 40 degrees for this angle. And when B was drawn over here, we're getting 40 degrees for this angle. So what's a conjecture that we could make here? So maybe a conjecture that you're making is that the inscribed angle, if we're using our new vocabulary, so the inscribed angle equals maybe half of this arc. And the same arc, right? Because they're each going from C and Q. So if the central angle is made from the same arc, it appears that it's half the amount. Or you could maybe be thinking that the arc is double the angle. So let's actually take a look at this conjecture and see if it continues to work. So here's a little applet, and we've got the angle measures shown. So the central angle is 96, which then we would know the same as this arc. And then here's the angle. So as I move B, you'll notice that the angle measure isn't changing. So no matter where point B is along this arc, and can I change it? Certainly, if I move this central angle. So let me change the central angle to 80 like we had. And then you'll notice that B stays 40. Okay, so as we change this central angle size, still appears to be half. Okay, so we got a 160, 180. So just some different measures there, but it appears that it just continues no matter where B is and no matter what the size of the central angle is, you keep getting that this central angle is double, or this inscribed angle is half. All right, so let's look at a couple of these, and we just saw this on the other screen, on the other little applet activity. So in each of these diagrams, we see a couple of different things. Here we have an obtuse central angle. Here we have a straight central angle or a diameter. Okay, so we get a 180 degree angle. And here we get an angle that goes over 180. It's actually called a reflex angle. Okay, so it's over 180 degrees, bigger than a straight angle. And it still appears to be half. Okay, so 180 to 90, 130 to 65. So you can put this on your reference chart. So pause the video, get this written down, that an inscribed angle is half the measure of the central angle. And it has to be defined by the same arc. So coming off the same arc, the inscribed angle is half the central angle. And the other way to think about that is the central angle is 2 times the inscribed angle. All right, then this is on page 153. So let's go ahead and label the diagram before we get started here. So it asks us to label the highlighted arc from point C to point E as 100 degrees. And then it asks us to label the arc from point B to D that's highlighted 140 degrees. Now we want to decide, can we prove that triangle CFD and triangle EFB are similar to each other? Okay, so here's triangle CFD, here's triangle EFB. Can we prove that they are similar to one another? And if you've forgotten how to prove that triangles are similar, here were the 3 ways that we learned to prove triangles are similar. Through angle-angle similarity by showing 2 pairs of angles are the same. Side angle side by showing 2 side lengths are proportional, 2 pairs of side lengths are proportional, and the angle between them is equal. Or to show all 3 sets of sides are proportional. So go ahead and try this, see if you can come up with how you would prove any of that. And then come back to the video and we'll talk about it. All right, so if we're going to go ahead and prove these two triangles are similar, okay? If we use some of the stuff that we just found out about inscribed angles would make some sense if we're learning inscribed angles. So if we take a look at this inscribed angle here, that's coming off this blue arc, right? So this one we just found out is half of the measure of this arc. So if this is 100, then we know this one is 50. And similarly, okay, we could look at this inscribed angle that comes off of that arc as well. And we could prove that this one is 50 also, because it's half of 100. So both of those two angles come off that 100-degree arc. And then you could be looking at a vertical angle. So we know this, and then that would be enough to prove the triangles are similar by angle. And you could certainly have used a different angle as well. So if you didn't use the inscribed angle from the blue arc, you could have used the inscribed angle from the orange arc. So we could have looked here. So we see this inscribed angle, which would be half of the 140. So you could have maybe seen that this was a 70-degree angle. And then similarly, E would be a 70-degree angle as well, since it is coming off of that intercepted or that orange arc as well. So however you decided to do that, whichever angles you decided to use, you could write that out as a proof. Okay, so you could do, let me get this started. So we know that the measure of angle D and the measure of angle B are both 50 because they are half of arc CE. And so this means angle B and angle B are congruent. Then we also know angle CFD and angle EFB are congruent because they are vertical angles. Therefore, triangle CFD is similar to triangle EFB by angle similarity. So that's just, I mean, obviously typing out the word, you could write out, you know, measure of the angle. When you're like for measure of angle D, you could be like measure of angle D equals 50 when you're writing it out. And if you used the angle C and E versus 9, you could substitute that in to your proof. So do we actually need to know the measures of these arcs, or could we do it without the measures? So we know that this angle, so let me do the ones that I did in my proof. Okay, so we know that this angle D is going to be half of this arc, whatever it is. I don't even need to know the measure, but I do know it's half of it. And then we're going to say angle B is also half of that same measure. Okay, so if I take whatever this number is here, I divide it by 2. When I take this and divide it by 2 again, I'm going to get congruent angles. B and D are going to be congruent no matter what this measure is. If this is 100, they're 50. If it's 80, they're 40. If it's 30, they're 15, etc. So I already know that these are going to be congruent no matter what. And then we've also got these vertical angles, okay, which you don't need a measure in there. We just know vertical angles are congruent. So without any measures, we still should be able to prove that those two triangles are similar by angle similarity. All right, then on the bottom of page 152, so turn back a page, you have this space down here. Draw yourself a circle. So take a compass and draw yourself a circle at the bottom of the page. And then use a note card or the corner of a piece of paper, or you'll need that. Okay, so draw yourself a circle and then get a note card or the corner of a notebook or a piece of paper. So then take your note card or whatever you have that's a 90-degree angle and set it on the edge of your circle. Okay, so that you can trace it. So I want you to trace it with, to get the angle here. So then just, let's see here. So just draw in this 90-degree angle. So just trace the edge of your card so that you have a 90-degree angle like that. And then connect the points where this crosses your circle. Okay, so where the angle extended to your circle, connect those 2 points. So you should have something that looks similar to this. All right, so what do you notice about the line that you drew that connected it? Okay, so did you notice it looks sort of like it cuts the circle in half, like it might be a diameter? Okay, so could that be a diameter, and can we prove that it's a diameter? So a diameter certainly cuts a circle in half, right? So the total of a circle is 360 degrees. So then a diameter is going to cut it into 2 180-degree arcs. So do we have that happening here? And the answer from this lesson is yes, because we know that this is 90 degrees. It intercepts here and here. So this arc, okay, so this angle right here should be half of this arc. So if we double that angle, then this would be a 180-degree arc, which means that this other part is also 180 when we subtract it from 360. So this segment definitely cuts the circle in half, meaning that it is in fact a diameter. All right, here's your lesson summary. You learned a vocabulary term today of inscribed angle, which is an angle formed by 2 chords that share an endpoint. So remember, they share this endpoint, which is their vertex. So that's their shared point. And it looks as though the inscribed angle is smaller. So we noticed that. And in fact, it's exactly half. So the measure of the inscribed angle is always half the associated central angle or arc. Okay, so once you draw in this central angle, that's equal to the measure of the arc. So if we know the central angle or the arc, these angles are half of them. So in this diagram specifically, they're telling us that this arc measure is 50. So if this is 50, then each of these little angles is going to be 25. So I just drew on a couple. I just drew this into my picture. But so each of those would be 25. And you can add this in, or you can draw it on this circle up at the top of the summary, but each of those would be 25. So all the inscribed angles coming off the same arc are going to be equal to each other. So hopefully after watching this lesson, you can use the relationship between central angles and inscribed angles to calculate angle measures. And you know that the inscribed angle is half of the central angle. You can check your understanding of this lesson by doing the practice problems for lesson 2. And if you need help or want to check your work, you can check out the video that I did going through those practice problems. And then we talked about what you would be able to do at the end of this lesson. So here it is, the measure of the arc from B to A, not going through C. So just from B to A, so right here is 30 degrees. Can you figure out the measure of angle BOA? Okay, so BOA is this one. Can you figure out the measure of angle BDA? So here's BDA. And can you figure out the measure of angle BCA? So go ahead and see if you understand what we did today. If you are struggling with this, make sure you reach out to your teacher.